Welcome back to the series on statistics. In this video, we're finally going to start taking a look at our first probability distribution. This is the binomial distribution. It is probably the most simple of the probability distributions, in my opinion. It's a discrete probability distribution that deals with statistical events that only have two outcomes. Typically, you would say the outcome is either a success or a failure, but you don't have to think about it in those terms. This could be any event that only has two outcomes can be modeled using a binomial distribution. So without further ado, let's get started. So one important caveat here is that these distributions rely on some assumptions that we're making. I'm going to talk about these assumptions at the end of the video after we have a sense of what a binomial distribution is and we get some sort of familiarity with it, because I think it's a little bit counterproductive, I would say, to try to start with all these assumptions about a distribution that we're completely unfamiliar with. So let's try to get an idea of what this thing is. And to do that, we're going to start with this question here. We looked at something similar to this in the last video, in my video on combinations and permutations, but imagine you're a stock trader who makes a total of 5 trades a day. Each trade has a 60% chance of being profitable, and in order to have a successful day, the trader must have made at least 3 profitable trades. And so what is the probability of the trader having a successful day? Well, there's basically 3 ways that the trader can have a successful way, or a successful day. And that's if all of their trades are successful, 4 of their trades are successful, or 3 of their trades are successful or profitable. Anything else, if the trader had 2 profitable trades, that would not be a successful day. The same with 1, and then obviously the same with 0. And so we are wanting to figure out what the probability of the trader having 5 successful days is, plus the probability of the trader having 4 successful days, plus the probability of the trader having 3 successful days. This is going to be the answer to our question. It's the sum of these probabilities. And so for this first probability here, the probability... actually, let's do this in a different color. If we're talking about this first probability here, the probability of x being equal to 5, or the probability of the trader having 5 successful trades, the only way that this can happen is if all 5 of the trades are successful. And since each trade is a chance of 60% for being profitable, then this is just going to be 0.6 to the power of 5. That one's an easy one. And then what's the probability of the trader having 4 successful trades, or this one right here? Well, you could imagine that this would be equal to the probability of 4 successful trades multiplied by the probability of 1 unsuccessful trade. This would be the probability of that happening. But how many different ways can this happen? We discussed this in our last video, but if you have 5 different possibilities, and we're looking at this case where we have 1 unsuccessful trade, but all of the other trades are profitable. This unsuccessful trade could be the first, but it could also be the second, or the third, or the fourth, or the fifth. And as long as all the other trades are profitable, then those are all different situations. It's 5 different distinct possibilities in which the trader could have 1 successful trade out of all the trades they made that day. And so each one of those, I might add, is going to have the exact same probability of occurring, because multiplication is communicative. So here, if I took 0.4 and multiplied by 0.6, by 0.6, by 0.6, by 0.6, that probability is going to be equal to this right here, because like I said, multiplication is communicative. It's exactly the same as taking 0.6 multiplied by 0.4 multiplied by 0.6 by 0.6 by 0.6. All of the probabilities of each of these outcomes is going to be equal, and it will be exactly equivalent to this right here, 0.6 to the power of 4. That is the probability of getting 4 successful or profitable trades, and this multiplied by 0.4 are the probability of 1 unprofitable trade. And so since there are 5 different ways that this can occur, and each of them has an equal probability given by this right here, then the total probability of the trader having 4 successful trades will just be 5 multiplied by the probability of that happening. So 5 different ways that could happen, multiplied by the probability of each one of those happening, seeing as how they're all equal. Now finally, let's deal with this situation right here. What is the probability of the trader having 3 profitable trades out of 5 profitable trades? What is this probability right here? Well, we saw in the last video, if we want to calculate the probability of this, we're going to have the probability of a successful trade to the power of 3, because there's 3 successful trades, multiplied by the probability of an unsuccessful trade to the power of 2, seeing as how in this situation there would be 2 non-profitable trades and 3 profitable trades. But then we need to multiply by the number of different ways that this can occur. And we saw in the last video that the number of different ways that this can occur is going to be exactly equivalent to the number of different ways that you could pull 3 positions out of a set of 5 positions. And we formulated we developed a formula in the last video to calculate this. And that's going to be 5 choose 3, which is just going to be equal to 5 factorial over 3 factorial times 5 minus 3 factorial. This is going to be 5 times 4 times 3 times 2 times 1 over 3. I'm going to rewrite this on the other side. 3 times 2 times 1. That's this 3 factorial right here. Multiplied by 5 minus 3 factorial. Well, that's just 2 factorial, so 2 times 1. This would cancel, and we'll be left with 5 times 4 over 2. So that's just going to be equal to 10. So there's 10 different ways that we could pull 3 different events out of a set of 5 events. So let's take this number, this 5 choose 3, the number of different ways that we can pull 3 events out of a set of 5 events, and let's multiply that by the probability of getting 3 successes, and that's going to give us the probability of that, and then we're going to multiply by the probability of 2 failures, because if we're choosing 3 events out of the set of 5, and we're multiplying that by the number of different, the probability of having 3 successes, then we need to multiply by the probability of having 2 failures to account for those remaining 2 positions that we didn't choose. So if you actually do the math here, and you calculate out these probabilities for each of these events, we see the probability of the trader having 3 successful trades in a day. This appears to be about 0.346. The probability here of this 4 successful trades appears to be about 0.259, 0.259. And then this probability here of having all successful trades seems to be about 0.078. And so if we take the sum of all these probabilities, we'll get about 0.683. And so this tells us that the trader has about a 68.3% chance of having a successful day. All right, so I've taken the liberty of filling out all of the possible outcomes that could occur. The trader here could have 5 profitable trades, 4, 3, 2, 1, or 0 profitable trades. And I've also gone through and written out all the work, rewrote it so it's all the same color, and I gave the associated probabilities with each of these possible outcomes. Now, if you go through and you sum up all of these probabilities, what you will find that there might be some rounding errors, so it might not be exactly equal to 1, but what you should find, especially if you were to plug in all of this information yourself into a calculator and to add up all of the results that you got so that they're exact and there's no rounding errors, is that all of these probabilities will add up to 1. And that should make sense. This is a discrete probability distribution. In other words, let's ask the question, what is the probability that the trader makes 3.5 profitable trades? Well, I encourage you to pause the video and think about this, but the answer should be obvious. The probability of this is going to be equal to 0. The trader can only make 1 trade at a time. They can't make half a trade. And so that trade is either going to be profitable or it's not going to be profitable. There's no other possibility, and there's no possibility of the trader making half of a trade, a quarter of a trade, or anything other than 1 discrete trade. Now, similarly, I should ask, what's the probability of the trader making 6 profitable trades? Here, once again, the answer, of course, is 0. The trader's only making 5 trades, so there's 0 possibility that the trader will make 6 profitable trades. And so with that in mind, all of the possible outcomes are listed right here. This is all of them. And so when you sum up all of the possible outcomes, that should give you a probability of 1, because one of these outcomes must occur. And so the reason that I'm going through all of this explaining is because when you have this situation where you have all of the possible outcomes of a certain experiment, in this experiment, you would say, is the trader making 5 trades with a 60% trades of each trade being profitable. When you have an experiment like that, you can model the probabilities of every single possible outcome, and it might be useful to do something like plot all of this information onto a graph. It's going to be, here, let's see if I can shrink it a little bit. It might be useful to plot all of this information onto a graph. Now here, you can start to see visually these bars, the heights of these bars represent the probability associated with each of these outcomes. So you can see here the probability of getting no successful trades is very, very low. It's about 1%, which is exactly what we have here. All I did was take this information and plot it onto a histogram in R. But this is just all of this information visualized. And here you can start to see it seems like the most likely situations a trader will make 3 profitable trades, but there's some wiggle room here. It wouldn't be that weird if the trader got 4 profitable trades, but generally, every day that the trader trades, they're going to be making trades within these boundaries here, between 2 to 4. It's very strange. You wouldn't expect the trader to make 5 or 1 or 0 successful trades, because all of these situations have a probability of less than 10%. It's very low. And so most of the time, you can expect that the outcome will be in this range here. Now, another way to say that, particularly due to the fact that we have all of the actual mathematical information here, is that the probability of the trader having a day that lands within this boundary here, between 2 and 4, or the probability of x being less than or equal to, or greater than or equal to 2, but less than or equal to 4, this is just going to be equal to the sum of these 3 values here, which happens to be, it's like 0.8354, 0.8354. So 83.5% of the time, the trader is going to have a day where they make between 2 and 4 successful trades. Now, what we are looking at here with this graph, or with all of this information on the left, whichever you prefer, is a probability distribution. This is a particular kind of probability distribution called a binomial distribution. But what a probability distribution is a representation of the outcomes of a statistical experiment. There's a lot of different definitions floating around on the internet, but this is what I think a probability distribution is. Sometimes people say it's a graph, sometimes people say it's a mathematical function, and I don't think it matters. Either way, it's telling you the same thing, just like all of this information on the left is just crystallized into a visual representation on the right. So a probability distribution is just showing you a representation of all of the possible outcomes of a statistical experiment, or maybe some of the possible outcomes of a statistical experiment. That is what a probability distribution is. Here on this graph, this is telling us a lot of information about what we would expect from this experiment, wherein we have 5 trials, each one with a chance of 60% for being profitable. And here I'm modeling the probability of having this many successful trades. This is the probability of having no successful trades. 1 successful trade, 2 successful trades, 3 successful trades, 4 successful trades, and 5 successful trades. And you could probably start to see how this information would be useful in real life to companies, businesses, maybe a stock trader. And although this is a very simplistic representation, you could think of constructing a distribution like this based on historical data. You could get the information such as the chance of a trade being profitable for a given hedge fund or a given investor, or whatever it might be, and you could construct a distribution like this, and that might be useful information to have. Of course, it's going to get more complicated than this, but you can already start to see where this might become useful. So what we're dealing with here is a binomial distribution. This is a particular kind of probability distribution that models an experiment within trials. In this case, there's 5 trials. And each one has a probability of p for success. Now here success is pretty arbitrary. Essentially all it's saying is that each outcome, each trial I should say, only is going to have two outcomes. Here, each trade that the trader conducts only has a chance of being profitable or unprofitable, and there's no other possibility. That is one of the conditions for a binomial distribution. The other conditions that have to be satisfied is that the trials need to be independent of one another. What happens in one trial cannot affect what happens in the other trial, otherwise it no longer becomes a viable model for representation, or a viable model for representing the possible probabilities of all the different outcomes. So all of the trials need to be independent of one another. If the trader has two successful trades and that makes him more likely for having more successful trades later on, then we can't use these calculations here because here we are implicitly assuming that every single trade has the same exact chance of being profitable. And we're also assuming that what happens in one trade does not affect what happens in the other trade. If you remember from our lesson on probability, when we have independent events, the probability of A and B is going to be equal to the probability of A multiplied by the probability of B. But this is only for independent events. If we have the probability of A and B for not independent events, and B, this is the probability of A multiplied by the probability of B given A. If we were dealing with a situation like that, then we wouldn't be able to apply these formulas because here we are assuming that the probability of B given A is exactly equal to the probability of B. We're assuming that all of these trials are not influencing one another. And if all of that starts to sound overwhelming, I'm going to review all of this in the end when we go over the assumptions of a binomial distribution and a couple other bits of information that we can pull out of those distributions. At this moment, what I want to do is return to what I said here, which is that the definition of success in these binomial distributions is arbitrary. Each trial in the binomial distribution can only have two outcomes. Here, the trade can only be profitable or unprofitable. There's only two possible outcomes. And in this case, we're modeling the probability versus the number of profitable trades. We could just as easily draw this distribution given the probability versus the number of unprofitable trades. And what you might expect, and what you might notice here, is that the chance of having 0 unprofitable trades is exactly the same as the chance of having 5 profitable trades. And likewise, the chance of having 0 profitable trades is exactly the same as the chance of having 5 unprofitable trades. These are exact mirror images of one another, so to speak, but you could just as easily draw the distribution here if that was more convenient for you or that fit what you were trying to present this data or information to. This is the exact same information, just crystallized into different representations. And there could be situations where one might be more appropriate than the other. It's important to understand that both of these are equally valid ways to represent this experiment. I think in this case I would prefer this one, but there could be situations where you might want to model the probability of having unsuccessful trades. There could definitely be situations where that would be more useful. All right, so summarizing all of this information, we have a couple assumptions that need to be made for a binomial distribution. One, we need to assume that the trials are independent of one another. If they weren't independent of one another, then what happens in one trial would affect the probability of what happens in the other trial, and this would violate our third assumption here, which says that each trial needs to have the same probability of success. These aren't exactly the same thing because you could have trials that have different probabilities of success because, for example, let's say in this trading example, trades that are conducted near the end of the day have a lower probability of being profitable. That has nothing to do with the other trials. But if you have trades that are profitable that are causing you to have more profitable trades, like maybe you're on fire or something, I don't know, that would cause the trials to have differing probabilities. And they need to all have the same probability of success, whether or not they're being influenced by other trials or if they're being influenced by environmental factors. Both of those will throw off the accuracy of a binomial distribution. And secondly, each trial needs to only have two possible outcomes. So all of these assumptions need to be true. And the reason that all of these assumptions need to be true is because we are essentially constructing this probability mass function for the distribution. Now, don't be thrown off by the name. It might sound a little bit complicated, but these functions just give the exact probability of a particular outcome of a statistical experiment in a discrete probability distribution. And so the PMF for a binomial distribution with n trials and a probability of success of p for each trial is this formula right here. The probability that x is going to be equal to k is equal to n choose k multiplied by the probability of success to the power of k multiplied by the complement of that, 1 minus p to the power of n minus k. And this formula, don't be thrown off by it. This is just exactly what we have been doing this entire time. This is all of these formulas right over here are just the application of the binomial probability mass function. I encourage you to pause the video and think about how these two things are the same. All the work that we're doing is exactly equivalent if you don't understand. But basically here, what we're saying is that the probability that x is equal to k is we're choosing k events out of n total events, right? And then we're saying the probability of success, we're taking that and raising it to the power of k because we want k successful events. And then we're doing the probability of failure, which because there's only two possible outcomes in each trial from our second assumption here, the probability of not being successful is just going to be 1 minus the probability of being successful. There's no other possible outcomes. You either succeed or you fail. You either have a profitable trade or you don't have a profitable trade. And so the probability of having an unprofitable trade or an unsuccessful trial is just 1 minus the probability of having a successful trial. And then we're going to raise that to the power of the remaining trials. We want k successful trials. How many other trials would there be? There'd be n minus k. So if you had 5 trials total and you wanted to have 3 successful trials, k would be 3, and then the exponent that you would want to have here on the probability of failure would be 5 minus 3, which is 2, because you want these two to add, you want these two exponents to add to give you n, so that you have a explicit outcome for each trial in your experiment. And so once again, if you need to pause and reflect on this, I encourage you to do so, but this is just what we've been doing this entire time. This is just a formal expression of it. This is called the probability mass function for a binomial distribution. And so if you wanted to break down the anatomy of this PMF just a little bit, just because I don't want there to be any confusion on this topic at all, you have this n choose k factor out front. Now this is giving us, from our combinations video, this is the number of ways that this outcome can occur. So typically there's many different possible ways for you to choose k events out of n total events, for you to choose k trials out of n total trials, and we need to factor that into our equation. If there's 100 different ways that you can have 3 events out of some number of total events, then we need to make sure that we're accounting for each one of those possibilities when we are accounting for the probability that we have k as our outcome, or k successful trials as our outcome. And then this in red here, we have the probability of a successful trial and another successful trial and another successful trial k times. And we learned from our probability rules that we are allowed to use this and rule so long as these trials are independent of one another. So long as we're dealing with independent events, then we know that the probability of one successful trial and another is just the same as multiplying those probabilities together, as long as each trial has the same probability of success and the trials are independent of one another. If these assumptions were not true, then we wouldn't be able to apply this line of reasoning, and we wouldn't know that the probability of one successful trial and another would be just simply equal to the product of all of those probabilities. So these assumptions need to be true for us to make this statement here in red that the probability of k successful trials is just the probability of one successful trial to the power of k. We need these assumptions. And then here in blue, we're saying that we're also saying, and we have the probability of an unsuccessful trial and another one for the remaining number of trials, or n minus k trials. And we know that this probability of an unsuccessful trial must be equal to 1 minus p, which is the probability of a successful trial, because of this second assumption here, that each trial only has 2 possible outcomes. And so in total, this whole statement here, this p to the power of k multiplied by 1 minus p to the power of n minus k, this is giving you the actual probability of this entire outcome. It's the probability of having a successful trial and a successful trial and a successful trial, or k successful trials, and the probability of n minus k unsuccessful trials, which is overall giving you the total probability of what you're looking for, which is k successful trials and n minus k unsuccessful trials. And so that's what we have here in pink, is the total probability of that actual outcome. And when you take the probability of that outcome and multiply by the number of ways that that outcome can occur, this is going to give you what you were looking for, which is exactly the probability that the number of successful outcomes is equal to k. So I hope that kind of clears things up and explains why we need to make these assumptions in order to apply this mathematical reasoning. But there's one more thing that's going to be useful, particularly when we're dealing with these types of problems in practice. And that's going to be this notion of a cumulative distribution function. So these functions, when evaluated at k, for example, they are going to give the probability of the outcome of a statistical experiment being less than or equal to k. So for example, the cumulative distribution function for a binomial distribution within trials and a probability of success of p for each trial would be given by the following. You have the probability of your number of successful trials being less than or equal to k is just going to be equal to the sum from I is equal to 0 all the way up to k to the probability mass function evaluated at I, which is, in a calculator, this is how you would evaluate this PMF. You don't have to type out this entire equation. There is a function in your calculator called Binomial PDF, where you input the number of trials and the probability and the number of successful trials, and it will give you the probability. And if you take the sum of these probabilities from 0, 1, 2, all the way up to k, this will give you the cumulative distribution function. Or if you didn't want to do all of that math, you could input on your calculator as well the binomial CDF function, which will give you exactly this right here. It will give you the sum of all of those. Or if you prefer not to use a calculator, you could just do the sum of this formula up here, evaluated at all of the possible outcomes less than or equal to whatever your input to the cumulative distribution function is. So once again, I encourage you to pause the video and think about this, but it's a lot less... I think this equation might be more intimidating than it actually needs to be. It's really just adding up the probability mass function for all of the possible outcomes that are less than or equal to your input. Now, why might that be useful? Let's say, for example, you want to ask the question in this example, in the trader example, what's the probability that the trader will have an unsuccessful day? Well, this will just be the binomial CDF, within trials. And so in this case, we're doing 5 trials and a probability of success of 60%. And this would be the cumulative probabilities all the way up to 2, because the trader needs to have 3 or more profitable trades in order to have a successful day. So this function is going to give you the probability of an unsuccessful day. And you don't need to do nearly as much math. You could just plug this equation into your calculator, and it will spit out the sum of x is equal to 0, which is this 1%, 0.077%, or not percent, but this probability, and this probability, and this probability. It will spit out the sum of all 3 of these. Or in other words, the sum of the probability mass function evaluated at all of the values less than or equal to 2. So at 0, 1, and 2. That is all this cumulative distribution function is doing. It is just summing up the probability mass function at all of the values less than or equal to 2 in this case. It's just a lot faster than adding them all up manually. It's also worth noting that we could use this cumulative distribution function for the binomial distribution in order to answer our original question here much quickly. What is the probability of the trader having a successful day? The trader is only going to have a successful or unsuccessful day in this situation. And so what we could do is we could just say, well, the probability of a successful day would be 1 minus the probability of an unsuccessful day, which we just saw how to determine. And so you could imagine that this is also, if 1 represents the sum of all of these possibilities, and we're subtracting the sum of these 3 probabilities, then what we're going to be left with is going to be the sum of these remaining 3 probabilities, and this is exactly what the successful day is going to be determined by, because he needs to make at least 3 profitable trades. If he does that, then it will be a successful day. And so now we don't need to add up all of these probabilities. We can just do 1 minus the cumulative distribution function evaluated at 2. This is going to give us the probability of an unsuccessful day, and 1 minus the probability of an unsuccessful day will give the probability of a successful day. Or if you prefer to think about it in this way, the sum of all of these bars is equal to 1. If we subtract off the sum of the first 3 bars, we'll be left with the sum of the last 3 bars. And the sum of these last 3 bars is the probability of the trader having 3, 4, or 5 profitable trades in a single day. And that is our condition for the trader to have a successful day. Right here. And so all of these are different ways to approach the same problem that could allow us to arrive much more quickly at an answer than if we were having to do all this mathematics every single time. Okay, so the last thing that we need to touch on in this video, which is very important, is going to be the mean or expected value and variance of these binomial distributions. And so back to our original example where we have a trader making 5 trades a day in the stock market. If their trade is profitable 60% of the time, we're asked to calculate the expected number of profitable trades that the trader makes in a given day, or the mean or expected value, as well as the variance. And so in order to solve this problem, let's just go over a little bit of notation, which might be unfamiliar. If we let x be a binomially distributed random variable with 5 total experiments and a 60% chance of success for each experiment, this is the way that you would notate that, then we are asked to find what the expected value of x is equal to. And this isn't going to be a very rigorous proof. I'm going to go over a rigorous proof in just a moment, but just to build some intuition, give us some understanding as to why the mean of this distribution might be equal to what it is. I don't think it's that big of a leap to suggest that the expected value of this entire distribution here would be equal to the sum across all of the experiments of the expected value of those experiments, and I'll just denote that with a y. I don't think that's a big leap in understanding. Now, I understand this isn't very rigorous, but what would be the expected value of each experiment? Well, each experiment is either going to contribute 1 positive value trade, 1 profitable trade, and that's going to happen 60% of the time, or it will contribute 0 profitable trades. And so it won't add to the total, and that's going to happen 40% of the time. These are the only 2 possible outcomes, so the expected value of each of these experiments is going to be 1 times the probability of success, 0.6, plus 0 times the probability of failure, 0.4. And if you add these up, you're just going to get 1 times the probability of success, which is just equal to the probability of success. And so if we were to write this, we would be summing, in general, across all of the trials, and there's n trials, some constant which happens to be equal to the probability of success for each trial, the probability of success of each individual experiment. And if you're summing a constant value, that would just be p plus p plus p plus p n times, which is just equal to np. So at least based on our intuition, we might expect the mean of this distribution to be equal to the number of trials multiplied by the probability of success of each trial. And if we put some numbers to that and we apply that to this situation, we would expect the mean of this distribution to be equal to 5 trials multiplied by a probability of success of 60%, and this is going to be equal to 3. And that certainly does appear to fit the data or to align with this distribution that we have drawn here. Now, in order to go about proving this rigorously, what we need to do is remind ourselves that the expected value, or the mean, is just going to be equal to the sum over all of the possible outcomes. So here I'll just index from 0 and go through all of the different trials. And then the expected value is going to be the sum over all the possible outcomes of the value of that outcome multiplied by the probability of that outcome occurring. So in this case, the value of that outcome would just be equal to I. So you'd start with the possibility of 0 possible outcomes, one profitable outcome, 2 profitable outcomes, etc. You go all the way up to n profitable outcomes. And then we're going to multiply by the probability of this outcome occurring. And the probability of that occurring is just going to be our binom PDF. With 5 I guess in general, we're going to talk with n trials, a probability of success of p, and we're evaluating this at I. And so what's this equal to? Well, we know an expression, or we know our formula for the binomial probability mass function. So this is just going to be I times n choose I. Then we're going to multiply by p, probability of success, to the power of I, multiplied by the complement of p to the power of n minus I. And now what I want to do is, because I have some intuition as to what I think the expected value of this distribution might be, what I'm going to try to do is I'm going to try to factor out an NP out of this expression over here. And so the way I'm going to go about doing that is I'm going to unwrap this n choose I expression here. I'm going to say sum from I is equal to 0 all the way up to n of I. And then what does n choose I mean? Well, that means n factorial over I factorial n minus I factorial. That's just what n choose I means. I'm multiplying by the probability of success to the power of I, multiplied by the complement to the power of n minus I. And where can I pull an n and a p out of this expression? Well, if I just decide to drop this down to n minus 1 factorial, then I could pull the n out of the expression. So this is just n times n minus 1 times n minus 2, dot, 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 dot. I could factor out this n, and I would be left with n minus 1 factorial. So I'm going to do that. I'm going to factor out an n from this factorial term here, and I'm going to bring it out front. I'm going to change this to n minus 1 factorial. It's not going to change the validity of this expression. And I can factor out a p just by dropping down this exponent by 1. This is p times p times p times p I times. If I pull one of those p's outside of this sum, and I drop this exponent by 1, it's similarly not going to change the value of this expression. So I'm going to make those two simplifications in order to factor out this np. And then the other thing I'm going to notice here is that this is I factorial in the denominator here. That's just I times I minus 1, dot, 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 all the way down to times 1. And what I'm noticing here is that I'm multiplying by I, so I could just cancel that here with this one, and I'll be left with I minus 1 factorial. So I'm going to make all of those changes to clean up this formula a little bit. And what I'm going to get is NP here, my expected result, my hypothesis. Oh, the other change I want to make here is that if I'm multiplying by I, this entire expression by I, if I'm starting at 0, this whole expression is just going to be 0. And since this is a sum, I could just start from 1, and this isn't going to change the value of this expression. So I'm going to start from I is equal to 1. It's not going to change the expression because when we start at 0, multiplying this whole expression by 0 and adding 0 to any sum is not going to change it. So we'll start from I is equal to 1, then. And because I factored out this n here, I need to drop this to n minus 1 factorial. And similarly, because I factored out this I with this I factorial in the denominator, I'm going to have I minus 1 factorial here. Then we're multiplying by n minus I factorial. And then here I need to drop the exponent on this p variable here because I pulled this p outside of the sum. And then I'm multiplying by the complement to the power of n minus I. Okay, so now let's get into trying to deal with what this remaining sum is equal to. What I'm noticing here is that this expression here, this is just equal to n minus 1 choose I minus 1. Why? Well, that would be n minus 1 factorial over I minus 1 factorial multiplied by n minus 1 minus I minus 1 factorial, and those negative 1s are going to cancel with one another. We would just be left with n minus I factorial. And so I can make that adjustment, and I could say that this is just going to be equal to np times the sum from I is equal to 1 of n minus 1 choose I minus 1 p power of I minus 1 of 1 minus p power n minus I. And while it might not be immediately obvious, I think we are basically done here, because with a clever substitution of variables here, if I just say, for example, if I let j equal n minus 1, and I let k equal I minus 1, how would that change this sum here? Well, we would still have the np out front, it would remain unchanged. And then we would start indexing from, let's see, we want I is equal to 1. When I is equal to 1, k is equal to 0. So we would start from 0. And now we can't, you might think that we need to index to j plus 1, because that's what n would be equal to given this expression. But if we index all the way to j plus 1, we're essentially going to be adding an extra term to this series. And so we need to, in order to preserve the number of terms in the series, we need to index to j. And if you don't believe me, go through and go to the first term of this series and the last term of this series, and the first term of this resulting series I'm about to write out, and the last term of that series. Calculate what those would be equal to, and you'll see that it is definitely necessary we need to index to j, not j plus 1, in order to make sure that these series are equal to one another. But with that being said, we have j choose k now. That's what we're going to have here. And then we have p to the power of k multiplied by 1 minus p to the power of j minus k. And now, I think we are done here, because this expression right here is just equal to the PMF, the probability mass function for a binomial distribution. That's exactly what this formula is equal to here. And essentially what we are doing here is we are summing all of the different possibilities, all of the different probabilities from 0 all the way up to j. And if you sum up all of the possible probable trades, for example, if you sum up all of the different probabilities of success for each of the experiments, you're just going to be equal, it's just going to be equal to 1. You're adding together all of the possible outcomes of the binomial distribution. And we already determined that if you add together all the possible outcomes, that at least one of those outcomes must occur. So you're going to have a probability of 1 if you add up all of the possible outcomes. And so this entire series here is just going to be equal to 1. We're adding all the possible outcomes of the binomial distribution. And so this is just going to equal np times 1, which is just equal to np. And so this is a formal proof for the mean of the binomial distribution. All right, so we've determined our expected value. We determined that for binomial distributions, the mean or expected value is going to be equal to the number of trials multiplied by the probability of success for each trial, which in this case is 5 times 0.6, which is equal to 3, which lines up with what we see here and what our intuition was telling us. Determining the standard deviation, or the variance, is going to take a lot of the same steps, but it's going to require us to be a little bit more clever. And so recall that the variance, actually I should do this down here. Recall that the variance is going to equal the second moment, or the expected value of x squared, minus the first moment, or the mean, squared. And we know what the first moment is, so we really just need to calculate this here. And so the second moment is just going to be equal to the sum across all of the possible outcomes. So from here, we're going to index from I is equal to 0 all the way up to n again for all of the different experiments. And this time, instead of multiplying by I, we're going to multiply by I squared for the second moment. And once again, we have to multiply by the probability of I occurring. And so the probability of I occurring is just going to be our binomial, or our probability mass function for the binomial distribution, which is n choose I, multiplied by the probability of success to the power of I, multiplied by the complement of that probability to the power of n minus I. And so just as before, we want to simplify this a little bit. And the way that we're going to do that is we're going to unfurl this. And just as before, I'm going to cancel one of these i's with the I factorial in the bottom. And similarly, I'm going to pull out an n and a p just in the same way that I did it before. And I'm going to start the index from 1 instead of starting it from 0. Once again, because having this I up front, when we multiply anything by 0, it's not going to change the value of the sum. So we could just start from I is equal to 1. So we're making all of the same changes that we made before. The only difference here is that we're going to be left with an I in the expression here. And so here we're going to have n minus 1, choose I minus 1. The probability p to the power of I minus 1 is 1 minus p to the power of n minus I. Once again, we're taking all the same steps here that we did in the previous proof for the expected value of the binomial distribution. So if you're not sure what's going on, just go back and watch the first couple steps of that distribution. We're factoring out this n and this p here. So we're dropping down the exponent. We're dropping down this n minus 1, choose I minus 1 by canceling one of these i's with the I in the denominator, but it's all the same steps. Now, just as before, we're going to do a clever change of variables here. So I'm going to say j is equal to n minus 1, and let's do k again. K is equal to I minus 1. And then this is going to become np, once again, multiplied by the sum. This time we're going to be indexing from k is equal to 0. K is equal to 0, all the way up to j, just as before. And here we're going to have I is going to be equal to k plus 1. If you add 1 to both sides of this equation here, we'll get k plus 1 is equal to I. So we want to have k plus 1 here, since we're changing these variables. And here we have j, choose k, multiplied by the probability of success to the power of k, complement here, power of j minus k. J minus k. That's a bad j. Now what we can do is we can break this sum up into two separate parts because we have this k plus 1 here. So let's say that this is equal to np multiplied by, I'll leave myself some room here because we're going to go from k is equal to 0 to j of k multiplied by j, choose k, p to the power of k, 1 minus p to the power of j minus k. And then here we're going to add the sum. And this time we're just distributing this k plus 1. So this is just going to be 1 times this expression here. This one right here was just k times this entire expression here. That's what we got for this sum. Now we're doing the same thing but with 1. So we're just going to get the sum from k is equal to 0 to j of j, choose k, multiplied by p to the power of k, 1 minus p to the power of j minus k. Boom. And now, while this might look more complicated, this sum right here, this is just the sum of all the probabilities of the binomial distribution. And so this is just going to be equal to 1, just as before. And what about this sum here? Might not be as immediately obvious as this one, but really all we have here is the equation for expected value of the binomial distribution, except we change the variables here. So now we're no longer indexing from I is equal to 0. We're indexing from k is equal to 0 up to j. And so we know what the value of the expected value of the distribution is. It was np in our example when we index from I is equal to 0 up to n. And so the expected value here is just going to be equal to jp. You could think if we factored out the j and we factored out the p, then this expression here would reduce to 1, and we would be left with just jp. And so this is going to give us np times jp plus 1. And now the last thing that we need to do here is we just need to substitute what j is back into this equation right here. And so what we're going to get is np times n minus 1 times p plus 1. This is going to reduce to np times np minus p plus 1. And all of that is just going to be equal to np squared minus np squared plus np. And so let's remind ourselves here that this is equal to the second moment. And so what we have just computed is the second moment. If we want the variance, then what we need to do is we need to take this and subtract the first moment squared. And the first moment, once again, is NP. And so we need to subtract NP squared. NP, this is just being this is the first moment or the mean of the binomial distribution. When we subtract this, this will cancel this NP squared here. And we'll be left with NP minus NP squared. So this is NP minus NP squared. And this is just equal to NP times 1 minus P. So that's the variance of the binomial distribution. So if we take this newfound information and apply it to our original example with the trader making 5 trades with a 60% chance of success, and calculate our variance, we get 5 times 0.6, which is 3, multiplied by 1 minus 0.6, which is 0.4. Get 3 times 0.4 is 1.2, and this tells us that this probability distribution, this binomial distribution here, will have a standard deviation of about 1.095. And so with that, we've figured out how to calculate the mean and variance of binomial distributions. We figured out how to calculate the probability mass function for a binomial distribution and what that means. We calculated and explained what a cumulative distribution function for a binomial distribution is. And we talked about all of the assumptions that need to be in place for the mathematics of a binomial distribution to hold true. I hope you guys enjoyed this video, and I hope this gives you a glimpse of how statistics starts to get pretty interesting and exciting.